So Chapter 8, hypothesis tests. So hypothesis tests, this is what we've kind of been working up to the whole entire semester, is focusing on, can you guys see my screen? Yeah. Is hypothesis tests. It's all about hypothesis tests. So hypothesis tests, to test to see if your sample is unusual or not. So here, this is a two-tailed test because you can be unusual either to the right or to the left. And these would be what we would consider usual values. What's our general guideline for unusual again? Do you guys remember, generally speaking?
5% or less.
Yes, 5% or less. So that's our typical guideline for unusual. So typically this would be 95% inside of here. This is a one-tailed, I didn't do that yet. This is a one-tailed test, or two-tailed test, excuse me, because there's two tails. The left side and the right side both have tails. And then there are one-tailed tests, so like this one where we only care about something being over here to one side or the other side. In this case, it would be to the right. So everything over here would be considered unusual, and all this would be 95%. So this is 95% of the population, and this right here would be 5% would be all right in this little tail here. Good. So this is how it works. If the null hypothesis says my mean is the same as everybody else's mean, the whole world's mean. So, for example, if you guys remember a while back when I kind of tricked you all and I said, here, draw a card. If you draw a black card, you get a chocolate truffle, right? And the null hypothesis would say that my deck, my mean, is the same as everybody else's. So my deck would be the same as everybody else's deck. And then we take a sample. If my sample falls in the usual range, then I don't dispute that mine is the same as everybody else's. But if I get something that's really unusual for a sample, then I reject the null hypothesis and say that my mean is not the same as everybody else's mean. And that's what we did. We drew 6 cards, and they were all red cards. Red, 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 red. If my deck is the same as everybody else's deck, it's very unusual for someone to draw 6 red cards in a row. So instead, we rejected the null hypothesis and said that no, my mean's not the same as everybody else's. And you guys all said, Ms. Young, your deck is fixed. It's not 50% red cards. And instead it's something a lot higher than 50% because everyone's getting red cards. So that's the whole idea, is the null hypothesis says that yours is the same as everybody else's. So you get an unusual sample, then you reject the null hypothesis and say that yours is different somehow. We're going to do another quick practice with that, where, for example, a friend of mine gives me a coin, and he flips it 10 times. So if I flip a coin 10 times, how many heads do I get? What percent of heads do I expect to get? Anybody? What percent of heads do I? 50%. Right, so you expect 0.5 of them to be heads. So let's take a look at the Rossmann chance one-prop applet. So everybody Google, if you can. Some of you won't be able to because you've got Zoom going on there already. But go ahead and Google Rossmann chance applet. So I'm going to open up Chrome and do that. Rossmann chance applet. And one-prop applet helps too. But Rossmann chance applet. So Rossmann chance applet, and I'm going to pick the one proportion inference right here. You can also do it on your phone if you want to. So what's probability of heads? We said it's 50%. There we go. How many times did I flip the coin? So I'm flipping the coin how many times?
9.
I got 9 heads. I flipped it 10 times though. Are you guys with me? So I'm going to flip it 10 times. And then I'm going to turn off the animate and I'm going to do that. So it looks like I got 3 heads. And everybody see down here on the bottom where a little dot appeared where 3 is? If I draw again, I got 5 heads. So a little dot appeared where 5 is. If I kind of do that a couple more times, you'll see this is kind of where all the draws are going. So I want to do, I've done it 6 times. I want a total of 1,000. So I'm going to do 994 more times. So I have a total of 1,000. And this is what it looks like. You guys should have something similar to that. And we care about what proportion of them are 90% or more. So 0.9 or more. I'm going to count how many times that when I drew. So what I've done is I've flipped the coin 10 times over and over again. Here, let me reset. I'm going to flip the coin 10 times and see how many heads I get. I got 7. Flip it again for 70%. Flip 10 more coins. 50% of them were heads. Flip 10 more coins. So every one of these represents 10 flips of a coin and how many heads, what proportion of heads we got. So I'm going to do it over and over again. Each time I'm flipping 10 coins and counting what proportion of those were heads. So I'm going to do it 995 times more. So now I've flipped 10 coins 1,000 times. And out of those 1,000 times, how many of those 10 coin flips had 9 out of 10 heads, 90% heads? I got 13 this time. Last time I got 7 out of 1,000. That's less than this is 1.3%. Okay, did anybody get any other numbers? You guys all got something. Someone tell me what they got.
19 out of 1,000.
19 out of 1,000. So yeah, so that's less than 2%. 1 point something percent. So everybody got something in the range of less than 2%. Right, 1 point something percent typically, or maybe just under 1%. So again, my null hypothesis is that my coin is the same as everybody else's. So my proportion of heads should be 0.5. That's my null hypothesis. Mine's the same as everybody else's. We got about, we'll say about 1.5% of the samples had 9 or more heads. That's similar to what we call a p-value, and that was the probability of getting your sample. So the probability of getting 9 heads is 1.5%, because about 1.5% of them came up with 9 or more heads. So that's the probability. Is that unusual or not?
Yes.
Yeah, it's less than 5%, right? 5% or less is unusual. Since the probability of getting 9 or more heads is only 1.5%, that's super unusual. So, what do you guys think? First of all, is it possible that my coin is the same as everybody else's? Yes, I could get 9 heads. That could happen. But is it very likely? No, it's not likely at all. There's only 1.5% chance that I'm going to get 9 out of 10 heads. If I look at this, oh, did I close it? Accidentally, no, I didn't. Right? Only 13 times did I end up with 9 or more heads. I got 9 heads 13 times out of 1,000. That's unlikely. So it's possible. It happened 13 times out of 1,000, but it's unlikely. So do you think my coin is the same as everybody else's coin, or do you think my coin is somehow different? What do you guys think? My coin is different or the same as everybody else's?
Same.
So same? You think it's 50-50? It's going to come with heads half the time? If it comes up heads half the time, then I should have gotten, then the likelihood of getting 9 heads is 13 out of 1,000. I got 9 heads. I got 9 heads. I flip a coin. Okay, you guys focus. I flip a coin. Let me talk to you guys again. I flip a coin 10 times. I get 9 out of 10 heads. What is more likely? That I have a normal coin and I just happen to get 9 out of 10 heads, or my friend gave me a fixed coin, a weighted coin that comes with heads more often? What do you guys think?
It's a fixed coin.
It's more likely it's a fixed coin. 9 out of 10 heads is really unlikely. So, let me get back to this. Right, so because I got something unusual, something really unlikely, something's only going to happen 1.5% of the time. It maybe, yeah, I'm sure maybe I got lucky and I was one of those 1.5% of the times I got 9 out of 10 heads, but more likely my coin is a fixed coin. It's different. Right, it's not a regular coin because I got a very unusual sample. Again, go back to me bringing in that deck of cards. We got we got 7 red cards in a row. Getting 7 red cards in a row is super unlikely. It's much more likely that I gave you a fixed deck that was all red cards than it is that I had a normal deck of cards and you guys happen to draw 7 red cards in a row. Right? So if you get something unusual, if you get an unusual sample, then you're gonna, most of the time you're gonna reject H naught. Because it's more likely that reject H naught. It's more likely that you have something different. That my proportion of red cards was not 50%. My proportion of red cards was more like 100%. You guys get me? Yeah, so just to remind you guys, I gave a deck of cards. 7 people drew a card. They all drew red cards. Since the probability of drawing 7 red cards in a row is like 1%, then it's more likely that my proportion is not 50% red cards. Like I said, it's more like 100%. And you would reject H naught because H naught says that my deck is like everybody else's deck. Okay, so let's take a look at we're looking at here. So again, the null hypothesis says that my proportion is the same as everybody else's, the world's proportion. This P naught means the proportion of everyone, the general proportion. So since we got something that was really unusual, something way out here, then we're going to reject the H naught because we got an unusual value, which means that my P naught, so everyone take a look at this. Just look at it. See how this P naught is right here? If I took something in here, then I'm going to say, okay, that might just be due to variance. But if I get something way out here, then my proportion's probably not way over there. My proportion's probably somewhere in this range over here somewhere, not way over here. It's got to be closer to this. It should be more centered around, like, it should be more like that or something like that. You guys see what I'm saying? It shouldn't be, my mean should not be way over there. So that's kind of what we're saying, is that if you get something really unusual, your mean's probably not there. Your mean's probably closer to where you are, somewhere in this range over here. And remember, this P naught, that's the population proportion. That's what everybody in the world has. So rejecting the null hypothesis means either you happen to get an unusual sample, and that will happen 5% of the time, right? 95% confidence, and 5% of the time you're going to get something over here. Or my population is different. Now, it's my coin is not the same. Or people who take my drug differ from regular people. It pushes them more towards this direction in some way. All right, so now we're going to talk about null hypotheses. Sarah, Kay, can you read?
Yeah. A statistical hypothesis is a claim about a population parameter, which may or may not be true. The null hypothesis, denoted by H, I'm not sure if that.
H naught? Sorry, H naught. I think this is the first top of your notes too, guys, just incidentally, so you know. Keep going.
Okay.
Denoted by H naught.
Is a statement that the value of a population parameter, such as proportion, mean, or standard deviation, is equal to some claimed value, i.e. there is no difference between two parameters. my mu equals mu naught, or my t equals t naught.
Perfect.
We test the null hypothesis directly in the sense that we assume it is true and reach a conclusion to either reject H naught or fail to reject H naught.
Nice. Well done. So H naught is this kind of knot, N-A-U-G-H-T. It's the English word. If you guys have ever heard of all is for naught, this is some English phrase, old English phrase, I guess. It means all is for nothing. So naught means nothing. Null also means nothing, right? Null means nothing. Nothing's in there. Null. Not, nothing. So this is the, and zero, nothing, right? This is the nothing hypothesis, which means that there is nothing of a difference. There is no difference at all. So no, nothing, no difference. If two things have no difference, if you and your friend take a test, and your test scores, there's no difference between your test scores, that means they're what? They're equal, right? If you and your friend both have, if there's no difference between your scores, then they're equal. So the null hypothesis means no difference, no difference. In other words, they're equal. So that means the null hypothesis will always, this is really important, always, always, always be equal. See, you have these equals right here? And we test the null hypothesis directly. So we assume it's true, we assume that they're equal, and either we find that we either are able to disprove that or we can't disprove it. That's kind of what we're down to. And we'll talk a little bit more about that later. We try to prove it wrong, and we either are able to or we aren't able to. The alternative hypothesis. Austin, can you read for us?
Yeah.
Thanks.
Alternative hypothesis. The alternative hypothesis denoted by H1 or HA is the statement that the parameter has a value that somehow differs from the null hypothesis. The symbolic form of the alternate hypothesis must use one of these symbols: greater than, less than, not equal to.
Right, exactly. Since the null hypothesis is always equals, then the alternative hypothesis has to be a different symbol. What's different than equals? Greater than, less than, or not equal to. It has to be one of those. So you guys do problem number 1 on your worksheet. Circle the ones that could be null hypotheses and box the ones that could be alternative hypotheses. So go ahead and take a minute and do those, and then I'll call on people randomly to give their answers. Okay, while I have you, I'm just going to double check. I'm missing Gabe, Carl, Justin, Joey, Samara, Andre said he was going to be here, Brendan says he wasn't going to be here, Patrick, and Brandon, correct? None of you guys are here? Okay, just double check. Was any of those people here? Gabe, Carl, Justin, Joey, Samara, Brandon, Patrick, Brendan, and Andre, but I think they told me they weren't going to be here. All right, so let's go ahead and go through these. Sonia, what did you get for the first one? Did you circle or box? Let me turn on the chat so I can see. Chat if you can't talk. Sonia? I can't hear you, so go ahead and just type it into the chat if you want instead. Circle? Okay. Circle, that's correct. Okay. Yep, it can be a null hypothesis. Kat, can you do this next one here? The second one. Catherine, Kat Martinez, are you still with us? Yeah, it is alternative. Correct. Good. And then the next one, Janessa. So Janessa, you can either say it or you can type it in. I don't care either one. Janessa Sanchez, still here? Rizzo, you want to go ahead and go instead? Oh wait, there she is, circle. Okay, so circle is a null hypothesis. So null is always null. Null means no or none. None difference. Is there none? So none difference. So there's no difference between two things. They should be equal. Are these two things equal? Or saying no? So then that would be, it's not a null hypothesis. It has to be the other thing. So Janessa, go ahead and tell me about what's this one then over here. Yep, that's also a box. Good. Oops, I can't draw a box apparently. Rizzo, the next one in the middle, this one here. Circle, good. And then Soraya, the last one. Yep, alternative, good. That's the box. Great. All right, so two-tailed tests. So all of them are going to have an H naught of mu equals mu naught. That's going to be true for every single one of them. The thing that differs is going to be the H1. For a two-tailed test, it's going to be mu is not equal to mu naught, because not equal to, how can things not be equal? So in other words, say if I said I do not have 2 dogs, if the number of dogs I have is not equal to 2, that means I can either have less than 2 over here, or I can have more than 2 over here. So that would be not equal to could either be less than or greater than. That's two-tailed. So some of your alphas over here, some of your alphas over there. Either one of these, this is considered unusual, this is considered unusual. You have both sides being unusual. We call those critical regions. You have two tails that you're concerned about, this tail and that tail. This one over here, you only care about this tail on the left. You don't care if it's over here on the right. You only care about it being over here. So this is what we call left-tailed, when it's less than. My mean is less than everybody else's. Left-tailed, less than, I want it to be over here. And then right-tailed is the opposite. I say that my mean is bigger than everybody else's. So I want it to be over here in this area. So very often our goal is to is our H1, because a lot of times we want to prove that something is different. Like we'll talk about it actually. Let me give you some more concrete examples. Hold on. Before we do that, just problem number 2 on your worksheet, indicate just the alternatives, because again, the null hypotheses are going to be present always. You're always going to have a null hypothesis. The thing that determines whether it's left, right, or two-tailed is the alternative hypothesis. So indicate over here, just right over the top of them, whether they are a left-tailed, a right-tailed, or a two-tailed. So go ahead and do that. take 30 seconds, and I will call on people in a minute. And just type in your answer, that'd be swell.